1-0, let's go. Okay, good morning boys and girls. Welcome to Mr. Mickleborough's Maths World. This is the way it is. Today I'm talking to you about, very briefly, about volumes of solids of revolution. Now we're going to build this topic up from the basics. We've got some quite straightforward examples and then we'll get to other examples in a little while. What am I talking about when I'm talking about volumes of solids of revolution? Let's illustrate it by an example. I'm saying that we're going to find a solid that's produced by rotating a straight line around the x-axis, and then we're going to do it to the y-axis. And what's going on here is that if I was to plot that line on a number plane, 2x plus 1, so it's a straight line and it's going to have a y-intercept of 1, isn't it? It would look something like that. We don't need to be bothered too much about what it looks like, but that line there is supposed to represent y equals 2x plus 1. And what we're saying is that between where x is equal to 0, in other words the origin, and 4, we are going to rotate this line around the x-axis. And so it's going to trace out, can you see, a solid. That solid, in fact, is called a frustum. Okay? Think of it as a lampshade or a truncated cone. Alright, so that's another way of viewing it, is that area, that trapezium, in fact, is going to be swung around 360 degrees to produce our solid. Our job is to find the volume, so it's going to be in terms of units cubed. Now, how do I do that? Well, there is a template that we use. It goes like this: volume equals pi, the integral of our limits, and what we do is this is an equation, so it's y squared. We're going to square the equation and integrate in respect of x. Now let me tell you a bit about the logic of what's going on there. Not much, but a bit. When I rotate, if we imagine that point, our extreme point on our line that we're rotating, you could see that it's going to map out a circle. And we know that the area of a circle is given by pi r squared, don't we? Pi r squared. But can you see the value of y, in this case, is the same thing as our radius of the circle from there to there. So, you know, if that was 4, well, we know what it is actually. If we substitute 4 into there, we'll get 9, won't we? So the radius is 9. So when it comes to our little template, what we're doing is we're summing up an infinite number of circles that have area pi r squared. There's your pi and there's your r squared. Okay? So it's a rather nifty and powerful thing we can do with calculus. Alright, so really what this is saying is square your function or your equation and evaluate the integral times it by pi. Okay? And so our example here was for the line y equals 2x plus 1. What do we do? Let's plug it in. And by the way, our limits were 0 and 4 inclusive. So our volume is simply equal to pi times our limits, times the integral, whose limits are 4 and 0, and we've got to square this. So 2x plus 1 all squared, because that's our radius, dx. And that's going to equal, let's just put it in calculus-friendly form. Oh, I don't need to put it in calculus-friendly form because I've got a linear factor in here. That means I can use a sort of chain rule for integration to evaluate that, and under normal circumstances that's what I'll do. But, you know, often we can't use that little trick of the trade, so let's expand it out. That's generally what you would have to do. So it's a perfect square, so it's the first term squared, which is 4x squared, plus twice the product of the inside terms. 2 times 2 is 4, times 1 is still 4, 4x plus 1 dx. And that is what we're evaluating, gentlemen, a fairly basic or routine integral. So, let's do that now. Let's do the calculus. So we're opening with square brackets, of course. Raise the index by 1, divide by the new index. Raise the index by 1, you can't see an index there, but there's an invisible 1 there, isn't there? And then for any constant, you just attach an x to that constant when you integrate it. So, long story short, we've got 4x cubed over 3. Our new index is 3. Plus, now, it's going to be 4x squared on 2, isn't it? 4x squared on 2. Can we just call it 2x squared? Okay, to cut out a bit of working out. And then plus x. Our limits, of course, were 4 and 0. I should say pi out there, and not so much equals. Therefore, volume equals pi times that. So that's a bit messy. Pi times that. Okay, so let's go. V equals pi out front. 0 is a gorgeous number. When we substitute 0 in, that all of that evaluates to 0. So all I've got to worry about is subbing 4 in. Now, 4 cubed is 64, divided by 3, plus 4 squared is 16, times 2 is 32, plus 4. Okay, what does that come to? Well, 64 times 428 is 256, divided by 3. So therefore, volume equals pi. 256 on 3. Now, I'm going to convert everything to thirds to make it easy. Here, I think that's what I want to do. I'm just checking this. 1632, correct, plus 4, yep. Plus 96. Why 96? I'm converting this to thirds. Okay, so I get 8, common denominator, plus 12. And I didn't need square brackets actually there, so let's round them off like that. Okay, so final answer is going to be this. 256 plus 96 is nearly 100, isn't it? So 356 take 4 is 352, plus 12 is 364. 364, yes. So volume equals 364 times pi on 3 units cubed. Now boys, when we do these problems, we like to leave pi in the answer. It's what we call exact form. A lot of students feel uncomfortable about that. They want to know, well, yeah, but what does that come to? Well, you know, pi is 3.14159 going on forever. So it's going to be, what, a bit more than 1,000, isn't it? Divided by 3, so that in fact really cancels that out. So it's a bit more than 364 units cubed. But we like to leave our answer like that. It's a volume problem, so our units are cubed. Okay? All right, can we pause that?